Welcome, everyone. I'm excited to kick off today's presentation. Today, we'll be exploring the fascinating topic of properties of bulk matters. This is the first slide, so I'll keep it brief. We'll go over some key concepts related to bulk matter properties, which are fundamental to understanding material behavior. Throughout the presentation, we'll cover different properties, their significance, and how they influence real-world applications. So, let's get started and dive into the world of bulk matter. Let's explore some key concepts in fluid mechanics that build our understanding of how fluids behave in different situations. Starting with pressure inside a drop or bubble, we see how surface tension influences the pressure difference across the interface. Moving on, we recognize the limitations of Bernoulli's theorem, which applies best to ideal, incompressible, non-viscous flows, but has constraints in real-world scenarios. We then differentiate between steady and unsteady flow. Steady flow remains constant over time, while unsteady flow changes, affecting how we analyze fluid motion. Terminal velocity is another fascinating concept. It's the constant speed a falling object reaches when gravity is balanced by drag. Viscosity plays a crucial role in fluid flow, describing a fluid's internal resistance to motion, which influences laminar versus turbulent flow patterns. The buoyant force, explained by Archimedes' principle, tells us why objects float or sink based on displaced fluid weight. Pascal's law highlights how pressure applied to an enclosed fluid transmits equally in all directions, fundamental in hydraulic systems. We also examine the variation of pressure with depth in a fluid, which is essential for understanding phenomena like water pressure in tanks and the design of dams. Pressure itself is a scalar quantity representing force per unit area, critical in all fluid statics and dynamics. Surface energy relates to the work needed to create a surface, explaining phenomena like droplet formation. Bernoulli's theorem, a cornerstone of fluid mechanics, links pressure, velocity, and height in flowing fluids, underpinning many applications. Reynolds' number helps us predict whether flow will be laminar or turbulent, which is vital for engineering designs. Stokes' law describes the drag force on small particles moving through viscous fluids, while the ascent formula and the effect of temperature on viscosity show how fluid properties change with conditions. The barometric pressure measurement with barometers reveals how atmospheric pressure varies with altitude and weather. The question of why water leaks faster from the bottom of a vessel illustrates how pressure increases with depth. Then, we consider the difference between compressible and incompressible flow, especially relevant in aerodynamics. The effect of contact angle of contact, determines how well a liquid wets a surface, affecting droplet behavior. Poiseuille's equation quantifies flow rate in viscous fluids through pipes, tying together many of these concepts. The cohesive and adhesive forces explain how liquids stick to themselves and to surfaces, influencing wetting and capillarity. Finally, temperature impacts viscosity, changing how fluids flow, and the hydrostatic paradox reminds us that the force exerted by a fluid depends on the container shape, not just the fluid's weight. All these points are interconnected, helping us understand the complex, yet fascinating world of fluids and their behavior in natural and engineered systems. Fluid mechanics is all about understanding how liquids and gases behave when they are either in motion or at rest. It covers a wide range of phenomena, from how water flows in a pipe to how air moves around an airplane wing. When we talk about fluid dynamics, we're essentially looking at fluids in motion, but interestingly, fluids at rest are just a special case of motion with zero velocity. So, fluid dynamics includes both moving and stationary fluids, giving us a comprehensive view of fluid behavior. Fluid mechanics, then, is the science that studies how fluids behave under different conditions, whether they're static or moving, and how they interact with solids or other fluids at their boundaries. This interaction is crucial because it influences everything from engineering designs to natural processes. And stepping back even further, mechanics is the fundamental branch of physics that deals with both stationary and moving bodies under the influence of forces. It's the oldest physical science, laying the groundwork for understanding how objects and fluids behave in our universe. All these concepts are interconnected, and understanding them helps us analyze and predict how fluids will behave in real-world applications, which ties directly into the broader themes of this presentation. Let's take a closer look at examples of fluids, specifically liquids and gases. A fluid is basically any substance that can flow, which means it can change shape easily under the influence of an external force. Unlike solids, fluids don't have their own fixed shape. They take the shape of their container. This characteristic is what makes them so interesting to study in physics and engineering. Understanding how fluids behave helps us design everything from water pipes to airplanes. So remember, the key idea here is that fluids are substances that flow and do not maintain a constant shape on their own. Let's focus on some fundamental concepts of fluid statics. First, when we talk about pressure in a fluid, it's important to remember that pressure is a force that develops on the surfaces of the particles within the fluid. It acts equally in all directions, which is a key point. Now, an interesting aspect here is that in a fluid at rest, there is no shearing stress. This means the fluid isn't experiencing any tangential forces that would cause layers to slide past each other. Instead, the only stresses present are normal stresses, which relate directly to pressure. Additionally, the fluid in this state can either be completely at rest or moving in a very uniform way, meaning there's no relative motion between neighboring particles. So, in essence, when we analyze fluid statics, we're looking at situations where the fluid is either stationary or moving uniformly without internal shearing forces. Understanding this helps us set the foundation for more complex fluid behavior. But at its core, fluid statics is about these pressure forces and the absence of shear stresses within the fluid. Now, besides the Pascal, other units we commonly encounter include the bar, ATM, KGF/cm2, and LBF/N2, which is also known as psi. These units are often used in different contexts depending on the industry or region. Since the unit Pa or Pascal is quite small for most practical pressure measurements, we often use larger units like the kilopascal, abbreviated as kPa, where 1 kilopascal equals 1,000 pascals. For even higher pressures, we use the megapascal MPa, which is equal to 1 million pascals. It's important to remember that the basic unit of pressure is the Newton per square meter, or nm2, which we call a pascal. Now, to define pressure more generally, pressure is the normal force exerted by a fluid per unit area. Essentially, it's how much force the fluid applies on a surface divided by the size of that surface. Understanding these units and definitions is crucial because pressure plays a vital role in the behavior of fluids and the design of systems involving fluid mechanics. This ties back to our overall theme of understanding how fluids exert force and how we measure that force effectively. Now let's talk about pressure below atmospheric pressure, which we call vacuum pressure. This is defined as Pvac and calculated as PATM minus Pabs. Essentially, when the absolute pressure drops below atmospheric pressure, we have a vacuum. Most pressure measuring devices are calibrated to read 0 at atmospheric pressure. This means they show the pressure difference relative to the atmosphere, which we call gauge pressure, represented as P gauge. It's the absolute pressure minus the atmospheric pressure. It's important to understand that the actual pressure at any point, regardless of how we measure it, is called the absolute pressure. This is the true pressure exerted by the fluid or gas at that point. So, to connect these ideas, absolute pressure gives us the real, total pressure. Gauge pressure tells us the pressure relative to atmospheric pressure, and vacuum pressure refers to pressures below atmospheric levels. Recognizing these differences is crucial when working with various pressure measurement devices and understanding the overall pressure environment in a system. Pressure has a magnitude, but it doesn't have a specific direction, which makes it a scalar quantity. That means when we talk about pressure at a certain point in a fluid, we're only concerned with how much force is being applied per unit area, regardless of the direction. An interesting point is that the pressure at any given point in a fluid is actually the same in all directions. So, whether you measure it pushing from above, below, or from the sides, the pressure remains constant. This uniformity is crucial because it helps us understand how fluids behave and how forces are distributed within them. Recognizing that pressure is a scalar quantity and is the same in all directions at a point helps us simplify many fluid mechanics problems and build a clearer picture of how fluids respond under different conditions. So let's look at how pressure relates to the height of a fluid column and its density. Essentially, pressure, which we denote as alpha, depends on these factors. The fundamental formula here is P equals F over A, which is the force divided by the area. But we can also express this as P equals A times rho G over A, which simplifies to P equals H rho G. This tells us that the pressure exerted by a liquid at a certain depth h depends directly on the height of the fluid column, the density of the fluid, and gravity. Now, to find the force exerted by the liquid, we consider the mass of the liquid in that column. The mass is the volume times the density, and the volume itself is the cross-sectional area times the height h multiplying that by gravity gives us the force. F equals R rho G. So, to sum up, the pressure at a depth h in a liquid is directly proportional to the height, the density, and gravity. And the force exerted by that column is a H rho G. Understanding these relationships is key to grasping how liquids exert pressure and force, which ties into the larger theme of fluid mechanics we're exploring today. Now, let's take a look at how the pressure below a certain point is greater than the pressure above it. Here, we define P at the bottom as the pressure at a specific depth, and P at the top as atmospheric pressure, which we denote as PA. The key idea is that the pressure increases with depth, and this is captured by the equation P equals PA plus the product of height, density, and gravity. So, mathematically, the pressure difference between the bottom and the top is given by P bottom minus P top equals rho times H times G. Since we know that pressure is force divided by area, we can express the forces at the bottom and top as P times A. That leads us to the equation P bottom times a minus P top times A equals rho times a times H times G. Rearranging this, we find that the difference in force between the bottom and the top is equal to rho times a times H times G, and if we think about force in terms of weight, it's essentially mass times gravity. So the force difference can also be viewed as the weight of the fluid column, which is the density times volume times G. This concept is fundamental because it connects pressure differences directly to the weight of the fluid column, illustrating how pressure varies with depth. Throughout this presentation, understanding this relationship helps us grasp how forces and pressures behave in fluids, which is essential for many practical applications. In the presence of a gravitational field, pressure increases with depth because more fluid is resting on the layers beneath. Essentially, the deeper you go, the greater the weight of the fluid above, which leads to higher pressure. Now, when we look at how pressure varies with depth, we can express it with this equation. P equals Pa plus H times rho times G here. Pa is the atmospheric pressure at the surface, so that's our baseline. The variable H represents the depth of the liquid below the surface. Rho, of course, is the density of the fluid, and G is the acceleration due to gravity. This relationship helps us understand why, as we go deeper into a fluid, the pressure keeps increasing. It's a direct result of the weight of the fluid above pushing down more as depth increases. So, in the context of the overall theme, understanding this variation of pressure with depth is crucial, especially when analyzing fluid behavior in different environments, whether it's in the ocean, a laboratory, or even in engineering applications. All right, let's explore how pressure increases as we go deeper underwater. We know that at the surface, the pressure is 1 atmosphere, which is about 100,000 pascals. Now, according to the hydrostatic pressure formula, pressure is proportional to the height of the water column. When we look at the calculations here, if we set rho GH equal to 100,000 pascals, and using a typical water density of 1,000 kilograms per cubic meter, we find that this corresponds to about 10 meters, or roughly 30 feet. So, as we descend into the water, the pressure increases by about 10 meters for every additional 100,000 pascals. Now, the question is, at what depth does the pressure double from 1 atm to 2 atm, or from 100,000 to 200,000 pascals? Since pressure increases linearly with depth in this scenario, the answer is straightforward. At about 10 meters below the surface, the pressure would double. This illustrates a key concept. Pressure in a fluid increases steadily with depth, and understanding this relationship is crucial for many applications, from diving to engineering. So, in summary, every 10 meters of water adds roughly another 100,000 pascals of pressure. That's a vital point to keep in mind when considering how pressure behaves underwater. Now, let's explore why the speed of water leaking from the bottom hole is larger. The key idea here is that pressure increases with depth. As you go deeper into a fluid, the pressure exerted by the fluid above increases as well. This means that water at the bottom experiences a greater pressure compared to water higher up. Because of this increased pressure at the bottom, the water is pushed out with more force, leading to a higher velocity or speed when it leaks from the bottom hole. This concept connects directly to our overall discussion of fluid dynamics and how pressure influences flow rates. So, in essence, the deeper the hole, the greater the pressure, and therefore the faster the water leaks out. This relationship is fundamental in understanding how fluids behave under different conditions of depth and pressure. Now, let's look at the normal forces acting on the different faces of the vessel. As shown in the figure, we have forces FA and FB acting on faces BAFC and ADFC, respectively, and FC on face ADEV. These forces are denoted by AE, AB, and AC. What's important here is understanding how these forces relate to the pressure exerted by the fluid. According to Pascal's law, the pressure applied to an enclosed liquid is transmitted undiminished throughout the entire liquid and to the walls of the vessel. This means that any change in pressure at one point in the liquid will be experienced equally everywhere in the enclosed system. It's a fundamental principle that underpins how hydraulic systems work, ensuring that forces are transmitted perfectly through the fluid. So, when we consider these forces on the vessel's faces, they are direct manifestations of this pressure being transmitted throughout the liquid. This concept helps us understand the behavior of fluids under pressure and is key to many applications in engineering and fluid mechanics. Now, let's talk about pressure in a fluid. The key point here is that pressure is the same at all points on a horizontal plane within a given fluid. This means that if you measure pressure at different spots at the same height, you'll find they are equal, regardless of where you are in that fluid layer. Another important concept is that in a fluid at rest, the pressure doesn't depend on the shape of the container. So whether the container is tall and narrow or short and wide, as long as you're at the same height, the pressure remains the same. This idea might seem simple, but it leads us into the hydrostatic paradox, which is a fascinating aspect of fluid behavior. Essentially, it shows that the pressure at a certain depth depends only on the depth itself and the fluid's density, not on the overall shape or volume of the container. Understanding these principles helps us see how pressure distribution works in real-world applications, from designing dams to understanding how liquids behave in different shapes of containers. It's a fundamental concept that connects to many areas of fluid mechanics. Now, let's look at this diagram of an inverted closed tube filled with liquid. You can see that the column of liquid is being held up by the pressure of the liquid in the tank. Near the surface of the liquid, the pressure is atmospheric pressure. This means that the atmosphere is actually supporting the liquid, holding it up against gravity. This principle is fundamental to how barometers work, which we'll explore next. Understanding this setup helps us grasp how atmospheric pressure can be measured and why it matters in weather predictions and other applications. Let's talk about atmospheric pressure and how it supports different columns of liquids. It can support a column of water that's about 10.3 meters high. But when it comes to mercury, which is much denser, specifically 13.6 times denser than water. The same atmospheric pressure can support a mercury column around 30 inches high. This is what we call a mercury barometer, which measures atmospheric pressure using that height of mercury. So, the key idea here is that atmospheric pressure is powerful enough to hold up these columns. And the height of the column varies depending on the density of the liquid used. This connection between pressure, liquid density, and column height is fundamental to understanding how barometers work. It's a great example of how pressure is everywhere around us, influencing even the height of liquids in these devices. Let's take a closer look at buoyant force. First, the density of water, which we denote as ρW, is a key factor because it affects how much upward force water can exert on an object. Remember, density is essentially how much mass is packed into a given volume. Next, we have the basic formula for force. F equals P times A, where P is pressure and A is the area. This shows how pressure differences across an object can create a force. This is fundamental to understanding buoyancy. Now, when an object is submerged, it has a certain mass density, which we call ρO. This density determines whether the object sinks or floats, depending on how it compares to the water's density. Putting it all together, the buoyant force arises because the water exerts an upward pressure on the submerged object. The greater the difference in density and the larger the submerged volume, the stronger this force becomes. Recognizing this helps us understand why objects float or sink, and it ties into the overall theme of how fluids interact with solids. So here we see that the water exerts a force on the object in two ways. It pushes down on the top of the object and pushes up on the bottom. The key idea is that the difference between these two forces, the upward force and the downward force, is what we call the buoyant force, or FB. Now, because the pressure of water is greater at the bottom of the object than at the top, the upward force ends up being larger than the downward force. This means the buoyant force is directed upward. Understanding this difference is crucial because it explains why objects float or sink in water. The greater the difference in pressure, the stronger the buoyant force, which helps objects stay afloat. This concept ties back to the overall theme of how fluids exert forces and influence the behavior of objects immersed in them. Let's break down Archimedes' principle. The buoyant force, or the upward force exerted by the fluid, can be understood as the mass of displaced water multiplied by gravity. In other words, it's the weight of the water that the object pushes aside when submerged. Mathematically, this is expressed as the density of water times the volume of the object times gravity. So, if you see it written as ρW times the volume times g, that's what it means, the weight of the displaced water. Another way to look at it is by considering pressure differences. The pressure at a certain depth is related to the density of the fluid, gravity, and the height of the fluid column. The pressure difference across the object is ρWgh, where h is the depth. This pressure difference results in an upward buoyant force, which can also be expressed as the pressure times the area. So, ρWgh times the cross-sectional area, this highlights how the force depends on the fluid properties and the geometry of the submerged object. In summary, Archimedes' principle tells us that the buoyant force equals the weight of the displaced water, linking fluid pressure, density, and volume in a very elegant way. This principle is fundamental in understanding why objects float or sink and is a key concept in fluid mechanics. So the object will float if the buoyant force is enough to support its weight. That means, for an object to stay afloat, the upward force from the water needs to balance its downward weight. Now, the object will displace just enough water so that the buoyant force equals its weight. Essentially, it's the water's push-up force matching how heavy the object is. If it displaces as much water as possible, but this doesn't match its weight, then it will sink. In other words, if the displaced water isn't enough to support the object's weight, it can't stay afloat and will go under. One key point to remember is that objects with a density less than water will always float because their overall weight is less than the water they displace. This is a fundamental concept that links directly to understanding why some objects float while others sink. Now, let's talk about a very important property of liquids, which is called viscosity. Viscosity is essentially the property that describes how a liquid resists flow. It comes into play due to an opposing force, known as internal friction, that occurs between different layers of the liquid when there is relative motion between them. So, whenever one layer moves over another, this internal friction acts against that motion, making the liquid flow more or less easily. The higher the viscosity, the more resistant the liquid is to flow. This concept is crucial because it influences how liquids behave in various situations, from everyday activities like pouring syrup to industrial processes. Understanding viscosity helps us grasp why some liquids flow smoothly and quickly, while others are thick and sluggish. It's a fundamental property that ties into the overall behavior and characteristics of liquids we observe and utilize in real life. Let's talk about the coefficient of viscosity, which is pronounced eta. It's essentially a measure of a fluid's resistance to shear deformation. To put it simply, it's defined as the ratio of the shearing stress, which is the force per unit area, to the strain rate, or how quickly the fluid is deforming. In terms of units, the SI unit for viscosity is the poisoule, abbreviated as PL. However, you'll also see it expressed in other units like Newton seconds per square meter, which is NSM2, or equivalently, Pascal seconds, Pa-S. Now, looking at its dimensions, the coefficient of viscosity has the dimensional formula of ml-1t-1. This helps us understand how viscosity relates to mass, length, and time in a fundamental way. Overall, understanding viscosity and its units is crucial because it connects the microscopic properties of fluids with their practical, measurable behavior. It's a key concept that bridges the theoretical and experimental aspects of fluid dynamics. Now let's look at how temperature affects viscosity. For gases, the viscosity actually increases as the temperature goes up. So, when you heat a gas, its viscosity tends to rise, and conversely, it decreases when the temperature drops. We can think of this as a direct relationship, represented as eta increasing with temperature, or alpha. On the other hand, liquids behave quite differently. Their viscosity decreases as the temperature increases. When you heat a liquid, it flows more easily, meaning its viscosity drops. Conversely, cooling a liquid makes it thicker and more resistant to flow, so the viscosity increases with a decrease in temperature. This inverse relationship is crucial to understanding fluid behavior in different thermal conditions. Connecting this to our overall theme, these temperature-viscosity relationships are key in designing systems involving fluid flow, whether in gases or liquids. Knowing how viscosity changes with temperature helps us predict flow behavior and optimize processes in engineering and industrial applications. According to Stokes' law, the viscous drag, which we denote as F, is the force exerted by the fluid opposing the motion of a spherical object. When this object, with radius r, is moving through the fluid at its terminal velocity v, the drag force can be calculated. The law states that F equals 6 times pi times the viscosity of the fluid, eta, times the radius r, and the velocity v. This equation, F equals 6 pi eta of, is fundamental because it helps us understand how the fluid's viscosity and the size and speed of the object affect the resistance it experiences. It's especially important in studying particles settling in fluids or designing systems involving fluid flow. Connecting this to the overall theme, Stokes' law gives us a clear quantitative way to predict how objects move through viscous fluids, which is crucial in many practical applications, from engineering to biological systems. Let's talk about what happens when a body is dropped into a viscous fluid. Initially, the body accelerates due to gravity, overcoming the fluid's resistance. As it speeds up, the viscous drag force increases. Eventually, a point is reached where the downward gravitational force balances the upward viscous drag force. At this stage, the acceleration drops to zero, and the body continues to fall at a constant velocity. This steady speed is what we call the terminal velocity. The key factors influencing this are the radius of the spherical body, the viscosity of the fluid, as well as the densities of both the fluid and the material of the body. Understanding terminal velocity helps us predict how objects behave in different fluids, which is essential in many scientific and engineering applications. Now let's look at the concept of transitional flow. This is a flow pattern that alternates between being laminar, which is smooth and orderly, and turbulent, which is chaotic and disordered. It's like the flow switches gears, sometimes gliding smoothly and other times becoming more chaotic. Moving on, turbulent flow is characterized by highly disordered fluid motion. This usually happens at high velocities, especially with fluids that have low viscosity, such as air. When the fluid speeds up, the flow becomes turbulent, with lots of velocity fluctuations and swirling motions. In contrast, laminar flow is all about smooth, layered motion. The fluid moves in parallel layers without mixing much. High-viscosity fluids, like oils, tend to stay in this laminar state, especially at low velocities, because their thicker nature resists chaos. Understanding these differences helps us grasp how fluids behave under various conditions, which is key to controlling and predicting flow in engineering applications. Whether we're designing pipelines or aerodynamic surfaces, knowing when flow is laminar or turbulent influences our choices and outcomes. Now let's take a closer look at where this equation applies, with K equal to pi divided by 8. When we talk about Poiseuille's law, what we're really describing is how the volume of liquid flowing through a capillary tube depends on several factors. First, it's directly proportional to the pressure difference, which makes sense because the greater the pressure difference, the more fluid is pushed through. Next, it's proportional to the fourth power of the radius of the tube, which highlights how sensitive flow is to even small changes in radius. This means that increasing the radius significantly increases the flow rate. Conversely, the flow is inversely proportional to the viscosity of the liquid, meaning that more viscous fluids flow more slowly. Lastly, the flow decreases as the length of the tube increases, since a longer path creates more resistance. Altogether, this relationship helps us understand how various physical properties influence fluid movement in capillaries, tying back to the broader theme of fluid dynamics in biological systems. In the case of an incompressible liquid, where the density ρ1 equals ρ2 and both are equal to ρ, we have the relation A1V1 equals A2V2, which we can simply write as AV. This is known as the equation of continuity, and it tells us that the product of the cross-sectional area and velocity remains constant along the flow. Now, regarding flow types, if the Reynolds number R is less than 1,000, the flow of the liquid is streamline or laminar. That means the fluid particles move smoothly in parallel layers without mixing. On the other hand, if R exceeds 2,000, the flow becomes turbulent, characterized by chaotic and irregular motion, with mixing occurring across the flow. And in the intermediate range, where R is between 1,000 and 2,000, the flow is considered unstable. In this zone, the flow can switch between laminar and turbulent, depending on disturbances or changes in conditions. Remember, the critical velocity is a key concept here, because it marks the threshold at which flow transitions from laminar to turbulent. The parameters involved, density ρ, viscosity eta, and tube diameter d, affect the Reynolds number and consequently the flow regime. Understanding this helps us predict flow behavior in various engineering applications, ensuring systems operate efficiently and safely. When we talk about the term periodic, we're referring to a type of unsteady flow where the flow oscillates around a steady mean. In other words, the flow pattern repeats itself over time, showing a regular fluctuation rather than a constant change. On the other hand, the term uniform suggests that there is no change in the flow with respect to location within a specific region. So, in a uniform flow, the flow properties are the same everywhere in that region. Now, it's important to distinguish between steady and unsteady flow. Steady flow means that the flow parameters at a specific point do not change over time. In contrast, Unsteady flow involves variations at a point with time, which can be periodic or otherwise. Understanding these terms helps us analyze and predict fluid behavior in various engineering applications, ensuring we can better control and optimize flow conditions in systems like pipelines, turbines, and aerodynamic surfaces. Let's take a look at the different flow regimes based on the Mach number. When the Mach number, or ma, equals 1, we're dealing with sonic flow, meaning the flow speed is exactly equal to the speed of sound. If ma is less than 1, that's subsonic flow, so the flow is slower than sound. When ma is greater than 1, we're in the supersonic flow regime, where the flow exceeds the speed of sound. And if ma is much greater than 1, say ma 1, we're in the hypersonic flow regime, which involves extremely high speeds. Now, when analyzing systems like rockets or spacecraft that involve high-speed gases, expressing the flow speed through the Mach number helps us understand and predict the behavior of the flow. Next, let's talk about compressible versus incompressible flow. Compressible flow occurs when the density of the fluid changes significantly during flow, which is typical in high-speed gas flows like those in rockets. In contrast, incompressible flow happens when the fluid's density remains nearly constant throughout the flow, which is usually the case with liquids moving at relatively low speeds. Understanding whether a flow is compressible or incompressible is crucial because it influences how we model and analyze these systems. High-speed flows are generally compressible, requiring specific equations and considerations, whereas low-speed flows can often be treated as incompressible for simplicity. Now let's take a closer look at Bernoulli's theorem, which is a fundamental principle in fluid dynamics. At its core, Bernoulli's theorem explains how the pressure, velocity, and height of a moving fluid are related. It states that along a streamline, the total mechanical energy remains constant, meaning that if the fluid's speed increases, the pressure decreases, and vice versa. This inverse relationship between speed and pressure is what allows us to understand many everyday phenomena, like how airplanes generate lift or how a Venturi tube works. It's a key concept because it connects the behavior of fluids with energy conservation principles. When we think about the overall theme of fluid mechanics, Bernoulli's theorem helps us see how energy transforms within a flowing fluid, providing insight into both natural and engineered systems. Now, let's explore some key applications of Bernoulli's theorem. This principle isn't just theoretical, it has practical uses that impact our daily lives and engineering solutions. One major application is in fluid flow measurement, where devices like Venturi meters and orifice plates use Bernoulli's principle to determine flow rates accurately. These are essential in industries such as water supply, oil and gas, and manufacturing. Another important application is in aerodynamics, especially in the design of airplanes. Bernoulli's theorem explains how the pressure difference over the wings generates lift, enabling aircraft to fly. Additionally, it's used in the design of carburetors in engines, where it helps mix fuel and air efficiently for combustion. Overall, Bernoulli's theorem connects the physics of fluid flow to real-world engineering and technological advancements, reinforcing its significance across various fields. In this slide, I want to highlight some important assumptions we make when dealing with liquid flow. First, we often assume that all the liquid particles move with the same velocity, which simplifies our analysis. However, in reality, particles near the center of the tube tend to move faster than those near the outer edges. This velocity variation is something to keep in mind for more detailed studies. Next, we assume that there is no energy loss as the liquid moves, meaning no energy is dissipated. But in practice, some of the kinetic energy is always converted into heat because of viscous forces within the fluid. This is an important factor when considering real-world applications. We also need to consider what happens when the liquid moves along a curved path. In such cases, centrifugal forces come into play and must be included in our analysis to accurately describe the flow. Lastly, for simplicity, we often neglect viscous drag in our calculations, assuming the flow to be non-viscous. This assumption makes the math more manageable, but it's important to remember that viscous effects do exist, and can influence the flow in real scenarios. Overall, these assumptions help us develop a workable model, but understanding their limitations is crucial when applying Bernoulli's theorem to complex situations. Let's take a closer look at cohesive and adhesive forces. These are fundamental concepts in understanding how materials behave at the microscopic level. Cohesive forces are the attractive forces between identical molecules within a substance, which hold the material together. Think of the way water molecules stick to each other. Those are cohesive forces in action. On the other hand, adhesive forces are the attractions between different types of molecules, like water molecules sticking to the surface of glass or other materials. These forces are crucial because they influence phenomena like capillary action, wetting, and adhesion. For example, when you dip a glass tube into water, the way the water climbs up the tube depends on the balance between cohesive and adhesive forces. If adhesive forces are stronger, the liquid will spread out and wet the surface better. Understanding these forces helps us predict and control how liquids interact with solids, which is essential in many engineering and manufacturing processes. So, in essence, the interplay of cohesive and adhesive forces shapes many surface-related behaviors we observe daily and in industrial applications. So, why is hot soup tastier than cold soup? Well, it all comes down to surface tension. When the soup is hot, its surface tension decreases, which means it spreads more easily across your taste buds. This wider coverage allows your taste receptors to come into contact with more of the flavors at once. As a result, you perceive the soup as more flavorful and more enjoyable. Essentially, the heat helps the soup activate more of your taste buds simultaneously, enhancing your overall eating experience. This connects to the broader idea that temperature can influence how we perceive flavors, making hot foods often seem more flavorful than cold ones. Now, let's talk about the potential energy per unit area of the surface film, which is known as the surface energy. Essentially, surface energy represents the amount of energy stored in the surface of a material due to its molecular structure. It's like the energy required to create a new surface or to increase the surface area. An important point to remember is that surface tension is numerically equal to surface energy. This means that the force we observe pulling the surface molecules together is directly related to the energy associated with those surface molecules. Understanding this relationship helps us grasp how liquids behave at interfaces and why surfaces tend to minimize their area. Connecting this to the broader theme, surface energy plays a crucial role in phenomena like wetting, adhesion, and capillarity, which are fundamental in many engineering and scientific applications. Now, let's look at the excess pressure inside different types of bubbles and drops. For an air bubble, the excess pressure is given by 2 times the surface tension divided by the radius, or 2T/R. This makes sense because the pressure difference is influenced by the surface tension acting on the curved surface, and the smaller the radius, the greater the pressure difference. For a liquid bubble, the situation is slightly different. The excess pressure is actually doubled, so it becomes 4T/R. This is because a liquid bubble has 2 interfaces, inside and outside surfaces, so the surface tension acts on both, effectively doubling the pressure difference compared to a single interface. Now, when we consider a liquid drop, which is just a single interface, the excess pressure again is 2T/R, similar to the air bubble. So, to summarize, the key point here is that the excess pressure depends on the type of interface and the number of surfaces involved. The more surfaces, like in a bubble with 2 interfaces, the higher the excess pressure for the same radius and surface tension. Understanding these relationships helps us grasp how surface tension influences the stability and behavior of bubbles and drops, connecting directly to the overall theme of how surface forces impact fluid behavior. Now, let's wrap up with an important concept called the angle of contact. When we look at liquids in a container, the shape of the meniscus tells us a lot about the interaction between the liquid and the container surface. If the meniscus is convex, meaning it curves outward, the angle of contact is obtuse, greater than 90 degrees. On the other hand, if the meniscus is concave, curving inward, the angle of contact is acute, less than 90 degrees. This angle is measured at the point where the tangent to the free surface of the liquid touches the wall of the vessel. It essentially indicates how well the liquid wets or adheres to the surface. Understanding this helps us predict how liquids behave in different containers, which is crucial in many practical applications. So, in summary, the angle of contact gives us insight into the wetting properties of liquids, linking the shape of the meniscus to the interaction between the liquid and the surface.